Good day, everyone. My name is Reuben McIntosh, and with me are Brielle Johnson, Dayja Young, and Mr. William Douglas Lau. And in our project, we worked on object recognition system using convolutional neural network. Over the years, researchers have proven that convolutional neural network has had an outstanding performance in detecting objects. Researchers use Python frameworks such as Keras, TensorFlow, and Kofi to test and create that CNN model. There are publicly available datasets that could be used to test and train our CNN model. In our project, we developed a CNN model that detects objects using a security camera, and we deployed the CNN model on a Raspberry Pi to lay a foundation of a centralized smart security camera system. So how does a convolutional neural network work? A convolutional neural network works by you training it with several types of images, or you can call them several classes, and then testing after you've trained your CNN model with several images, you then test your CNN model with a new image for it to be classified from the trained images. So for our method in building our object recognition system, the first step was that we selected a public available dataset, which was a CIFAR dataset, and after that we preprocessed that CIFAR dataset. Then for our third step, we trained our CNN model with the CIFAR dataset, and for our fourth step, we tested our CNN model with single images, or you can say new images from our security camera, and which all leads for us to build our centralized object recognition system. So for our CIFAR CNN architecture code, we have several layers in our CIFAR CNN architecture code. The first layer is our input layer. The input layer, what goes in there is our CIFAR preprocessed dataset, and also that preprocessed dataset is converted into a 2D matrix. After that, the next layer is our convolution max pooling layer, and also our ReLU layer. And what this layer does is that they do mathematical computations on the CIFAR pre-processed data. The next layer after our convolution and max pooling and ReLU layer is our flattening layer. The flattening layer converts our 2D dimensional CIFAR dataset into a 1-dimensional vector. And after that one-dimensional vector is transferred into our fully connected layer, which then gives the prediction of our image. So what is a CIFAR dataset? CIFAR dataset are collections of images that are used to train in machine learning. They consist of 60,000 32 by 32 color images in 10 classes with 6,000 images per class. In our in the development of our object recognition system, we'll be using this CIFAR dataset to train and test our CNN model.
Data preprocessing. Here's an outline of how we will preprocess data. Capturing the image with Raspberry Pi camera is the first step, and then we'll perform the necessary pixel operations to then use that output for the CNN input. Now when preparing the CIFAR type data, an additional step, and the image was captured with the Pi camera, the picture will need to be resized. As you can see, the larger dog image being 525 pixels by 510, it was reduced to 32 by 32 pixels with the help of the libraries for Python, to name a few: Python Image Library and OpenCV. Now, an extra step in data preprocessing is generating a binary file. Here we are. With the reduced image being 2D, it will have to be converted into a one-dimensional data array. And that 2D image will be divided into red, green, blue color channels. And in order to get that 1D array, multiply 32 by 32, the width and height, to get the red channel. And the green lines up with the value 2048 once you add another 1024 to that. And adding another 1024 to 2048, you will get 3072. Now the binary file will be was able to be made because the data array has been formed. This slide is to show how this process can be applied to any number of color images: image 1, image 2, and image n, so on and so forth. Using the values from the original image, we can normalize the values. The min-max scalar method will be the method used. X being the original image, and the minimum value, for reference to the following formula, is 0, and the maximum value is 255. Following this formula below, x minus the minimum value of x divided by the maximum value subtracted by the minimum value will help normalize this image. This image has now been normalized to a range between 0 and 1.
To set up the environment of our training model, we use the CNN code based on the TensorFlow tutorial. We set up PyCharm 2.7 as our developmental environment, and we use PyCharm as our IDE, and we use Anaconda as an open source environment. We use TensorFlow 1.14 as our library, and we use libraries such as TensorFlow datasets, NumPy, and Future. 6 batches are used to train the CNN model. 50,000 preprocessed images go through the CNN layers to train the model. 10,000 new preprocessed images go through the CNN layers to test the trained model and then to obtain the accuracy of the model. And then our accuracy of our code was 86%. That was obtained from the trained model. Saving the trained model. The CNN must save its own data after training so that the computer is able to act on what it has learned. Weights and biases are what's saved through the hidden layers of a CNN, and then it saves 4 different files: a checkpoint file, which is a protocol buffer, the data file, which contains the values of the variables, an index file, which identifies the checkpoints, and then a meta file, which contains the graph structure. You must reload the meta file before the checkpoint file because it has the graph structures that's in the checkpoint file. For single image testing, we manually inputted our own image. We ran the CNN with a single image instead of a batch of images to get the labels number as an output to determine the performance of the model. We also loaded the saved CNN model into Raspberry Pi to classify the single image. We deployed our CNN onto a Raspberry Pi to demonstrate that a pre-trained model can run on a very little memory and computation power device, a small CPU. We prepared the Raspberry Pi, the 3B+, for a Python environment by setting up TensorFlow 2.7 as our virtual environment. We installed TensorFlow datasets, NumPy, and OpenCV, and then we downloaded the pre-trained CNN to run the model for prediction of a new image. The reason why we deployed our CNN onto a Raspberry Pi and set up our own virtual environment was because the 2.7 environment originally did not recognize our CNN code. Here are our results from the laptop compared to the results from the Raspberry Pi. They both have the same checkpoint files, and they both also have the same prediction. For the Raspberry Pi, we had to actually manually input the checkpoint files that were saved from the laptop training from the CNN, and we also had to set up the virtual environment. So there's different codes that we had to run on the Raspberry Pi instead of just running a single code on the laptop. The laptop ran quicker than the Raspberry Pi because the Raspberry Pi has minimal storage. Here is an example of the single image test code running on a laptop. As you can see, it predicts 5. Here is an example of the single image input running on a Raspberry Pi. First, you must activate the virtual environment. Then through the virtual environment, you must go through the directory of the Python projects. Through the Python projects directory, you can command the single image input test to run. It takes longer on a Raspberry Pi because Raspberry Pis have less computational abilities.
So live processing, which is achieved through parallel processing. In live processing, we have two types of processes. The first process is our producer process, and the second process is our consumer process. In our producer process, as you can see in the image, the producer process captures pictures from the Raspberry Pi camera and stores it in the queue. And in our consumer process, the consumer process gets single images from the queue, preprocesses those images, and then gives a prediction of those images using the save trained CNN model.
Network design for a centralized system would utilize IP security cameras as part of an enterprise network. AI can be integrated to make the camera system smarter. For future work, we would develop a client-server centralized system. Clients, or the security cameras, would send data to the server. The server is a multi-threaded and handles multiple requests from several clients simultaneously. The client-server program can be developed using socket programming over UDP or TCP. There are two cases in which the future work can be considered. Case 1, complete centralization, meaning all clients send images to the server. The server handles all computations by running the save CNN. Overhead computation is on the server. The second case would be edge computing. Embedded the system co-located with the clients performing CNN prediction. Notification information from the edge are sent to the server. Reduced overhead of computations at the server. The server can be linked with an app or control monitor to notify system administrators. Now to my lesson plans and activities. Understanding tech behind the tools. The use of computers and information systems in a nurse's daily work has become commonplace. Because of this, and because implementation of these systems is accomplished so rapidly, there is often little time spent on evaluating or researching the impact on the job performance. By developing nursing-specific research to address nurses' unique needs, and by expanding current research from other areas of healthcare, students will begin to see more clearly the impact of technology in the work of the nurse and shed light on how, why a nurse uses or does not use these technologies in their work. The overall objective would be to gain a hands-on experience exploring computers and other components.